decay a bunch of time. So then I can think about in the case where we have a blend of 5 to 4 on field theory, so we have a lot of harmonic oscillators here coupled together by a 5 to 4 interaction. And then the thing that can happen if we actually try to add a quantum to the system, say that can be coming along here, the quantum be added, and it can collide with something, some other quantum, which is present in the thermal state, and we can have 2 different quanta come out. Okay? So this is a cartoon to have in mind for what's going to be driving thermalization in this weakly interacting 5 to 4 theory. We have a particle that we added, and if there were no interactions, then it would have just continued to oscillate. The 2-point function would not go to 0. But since we have interactions and there are extra quanta present in the thermal state, one of those contains the quantum we're interested in, and it can get locked out of its state. So the right way to analyze that, the decay of this thing, that coupling, the 5 to 4 theory, is to consider a response propagator, where we take the propagator is equal to the free propagator, plus the interesting physics here is actually contained in the smooth self-energy. This resums to something where we have this thing, which is the free answer plus self-energy. Okay? And as usual, the important part of this self-energy diagram for getting the decay of this correlation function will be the imaginary part of the self-energy. So very roughly, we're going to get a propagator which looks like k naught squared minus k squared, and then we'll be adding this self-energy. And the imaginary part of the self-energy is what shifts the pole of this propagator off the real axis and gives us an exponential decay. Actually, the right formula is that the function g of t will be like e to the minus gamma k t, where k is the momentum index for the particular oscillator that we're going to be correlating here.
This becomes a bit like the expression model here, right?
Here. Yeah, this is just the self-energy diagram. This is the self-energy. So this expression gives us the sum of all of these guys. This geometric series. No, so these are all smooth self-energies, and this equation will resum all of them. Yes. Yeah, so we imagine, let's see, okay, so, yeah, let me not comment further on that. Okay, so the answer for this gamma is equal to the imaginary part of the self-energy k plus bar energy. And the actual correct way to calculate the self-energy is a little bit annoying. You have to do it by calculating the 2-point function on the Euclidean circle, which represents the finite temperature state, and then you have to understand the correct analytic equation. I'm not going to go into that in detail because the answer is just so plausible, and really doesn't take that much to write. What we find for this sigma is that it's equal to the imaginary part of sigma. It's equal to, first of all, 2 powers of the coupling. The 2 powers of the coupling are because this diagram has one coupling here and one there, so it's proportional to the square. And there's a factor, a thermal factor, which I always have trouble remembering exactly why we have this thermal factor, so let me ignore this. And then a closed interval. There's 2 loop momenta, and these 2 energies, I'm going to define this in a second. For which this is behind the plan, all I'm writing here is an energy conserving delta function. And what this is here is this integral over these momenta, where this is the k, here we have particle 1, 2, and 3. Yeah, so 1, I'm referring to this particle. Oh, I'm sorry. Let me say, this one is N2. This one is 1 plus N3, this is N1. So what we have here is just representing the following factors. We're integrating over all possible quanta that are target quanta we can collide with in a way that conserves energy momentum. And we have factors of N1 here, that's reflecting the number of these quanta that are present in the thermal state. Then we have these factors 1 plus N2, 1 plus N3, those are the Bose factors for the final state of these particles 2 and 3. So the decay is determined by the integral over all possible things that our particle can collide with, and a sum over the final states of things that the collision can result in. So this is just basically saying, in equations, what this picture is saying, that we can lose the quantum in our initial state by colliding with a simple quantum. So the result of this calculation will be that the 2-point function decays at a very slow rate. If the coupling is small, this calculation is valid, but it decays in a way that's exponential. Roughly speaking, this is because the collision can happen at any time. So we get an exponential decay of roughly the probability that the particle that we inferred to begin with is still present in the state. So, okay, doing calculations, doing primitive finite temperature calculations is possible, but it's annoying. And going beyond perturbation theory and studying this problem where we don't have a weak coupling is really impossible. People don't have a lot of techniques for doing this. But it's widely believed that this type of exponential decay of correlation functions is a rather universal feature of normalizing quantum systems. There's another piece of evidence for this, which doesn't come from perturbation theory, which comes from numerical simulations of spin systems. So, for example, we can consider things simple spin systems like this one, like an Eigen spin system. Where these matrices here are the Pauli X, Y, and Z operators acting as a different tracing system. So this is an example of a nice chaotic spin chain, and enterprising people can take this type of thing and put it on a computer and exactly diagonalize the Hamiltonian matrix, and then construct the thermal state by taking the exponential of minus data times the Hamiltonian, and then inserting these operators, one at time t and one at 0, and computing the answer, applying this function of time. And what you get in this type of system is something that looks like exponential growth or exponential decay for quite a while. You can't go for very long time because the numerical problem, well, you can't study this in very large systems because if we want to study n spins, then we have to use the Hilbert space that is a dimension 2 to the n. And the matrices that we'll be looking at, like Hamiltonian or the thermal density matrix, are 2 to the n by 2 to the n matrices. And your computer will just run out of memory. So people can study, I think the state of the art for this is maybe 18 bits or something like that. So it's a very small system, but it's enough to see some of this crazy state dynamics. So these are things that one can do. One can study perturbation theory, you get a slow but exponential decay, and you can study small systems, small spin systems exactly, and there you get exponential decay for a while. And this type of information has led to the following kind of picture for what happens to the 2-point function. It should decay exponentially for a long time. I don't know what I'm drawing here. It's roughly exponential. And then at very late times, if the system has finite entropy, it should stop decaying and start oscillating. The reason it starts oscillating is because in a finite entropy system, the 2-point function is a sum of oscillating exponentials, and that type of a function, a finite sum, or let's say absolutely convergent sum of oscillating exponentials, can't really go to 0 at late time. At late time, it can be small, but it has to be oscillating. The value that people throw around for this sort of oscillating floor is a value which is about e to the minus x. So there are wiggles on a scale of about e to the minus x. And so the transition here happens at a time of about x. If we assume that the 2-point function is decaying exponentially for a time of order of entropy, it will get down to a size which is e to the minus x. And after that point, we imagine that it oscillates about this floor value. Okay. Yeah, I wanted to present an argument for the e to the minus x, but maybe I'll do that at some time. I might out on time at the end of the lecture today. Yeah, sorry, this is GMT, which is actually, this is interesting. This is that this is a case where it's slightly different to consider a pure state theta and a thermal ensemble. And the answer that one expects for a pure state is actually larger. It's e to the minus x over 2 for this final fluctuating floor value. This is the estimate value. Well, let's say the real part. We could go for the estimate value, but then hit better not negative. Okay, so this is a brief introduction to 2-point functions. The thing I want you to remember is that we expect them to decay, expect them to decay exponentially. We can analyze it in perturbation theory, we get a very slow decay, but we can't analyze it very well. Even if I say it's derivatively is annoying. Okay, the other aspect of thermalization that I'm going to discuss a little bit is this idea of a quench. So the 2-point functions are diagnosing what happens if we take an equilibrium system and perturb it a little bit. And a quench is asking a very different question. It's asking what happens if we take some state and excite it all of a sudden to some very high energy but very non-equilibrium state. So a model for this is a state Q, which is given by a product over X of some operators acting inside X on the day. So if we have, let's say, a lattice version of the system, then we can act at every site in the system with some local operator OX. Because we're acting everywhere in the system, we're going to raise the energy by an amount that's extensive. So we're going to turn this low energy vacuum state into some high energy thermal state. But it's going to be a very special kind of high energy state, where all the all of the quanta are sort of uncorrelated to each other. We have created them all out of nothing, independently at each fragment of the system. And then what happens under time evolution is they interact and collide, and the correlations become more nonlocal. There are two different types of quantities that one can imagine computing to diagnose the approach to equilibrium of this state 2. A nice one is to consider the entropy of a subsystem A as a function of time. Okay. So H equals 0. We just acted with these local operators, actually let's imagine local unitary operators on the vacuum state. So H equals 0, the subsystem entropy will be the same as what we have in a vacuum. So H equals 0, it'll be the same as what we have in a vacuum. So who can give me an idea of what type of entropy we should expect to have for a subsystem in a vacuum state? So suppose we have some region, is there some geometrical feature of the region that will tell us what to expect for the entropy in the vacuum state? Sorry. Yeah, the area. So we expect to have the entropy of the subsystem A at time 0 to be proportional to area of A. And this will be divided by UV cutoff. Okay, and at very late time, we expect that this thing will approach an equilibrium thermal state, and then what does one expect for the entropy? Okay, we're expecting an extensive entropy, something proportional to the volume. Okay, and now instead of being a UV scale, this would be divided by powers of beta, the thermal scale. So in between, there's an interesting thing that will happen where the entropy grows from something proportional to the area to something proportional to the volume. And this is something that really cannot be computed. It actually hasn't even been computed how this happens in perturbation theory. The one case where it's been analyzed purely in field theory is the case of a single interval in a 1+1 dimensional field theory, where Celebrate and Carty showed that this is completely determined by conformal invariance, and that what happens is the entropy increases linearly from the area answer to its volume answer, and then it saturates. In general, though, this is much harder to calculate than these two-point functions, but the time dependence of this function for t less than 0 less than infinity is an interesting probe of thermalization. How rapidly these correlations become non-local. Yeah. Could you say that again? Oh, yeah, so no, the entropy makes sense for any system. For any state, it's just minus the trace of the density matrix times the log of the density matrix. So FA of t means the following. We compute rho A of t. That's equal to the trace over A complement of the state we have, which would be e to the minus I h t. Q to I h t. Okay. So this gives us the density matrix for subsystem A. And then we compute SA as a function of time, which is minus trace rho A log rho A. Yeah, so by entropy here, I mean the one-moment entropy, which is defined for any state. Okay. Yes. Yeah, well, one expects it to be monotonic. Actually, one expects also that at early times it should grow linearly. Although I'm not sure that one expected that before it had been calculated using black holes. So, sorry? Yeah, but the type of function one expects for this is, one expects this. I'm getting not drawn with this thing. One expects something like this. That's the volume answer. And here I'm plotting f of t minus x of 0. So this is the type of curve one expects, and properties of this thing, like for example the initial slope, that will be interesting diagnostics of the thermalization property of the system. Yeah, in principle, one would like to be able to calculate the slope, let's say, to a leading order in a coupling in a weakly coupled field theory, but I don't think anybody knows how to do that. It looks like a very difficult problem. Okay, so that's the introduction to thermalization without black holes. We discussed the two-point function, where we can use perturbation theory, or we can use exact diagonalization. We also discussed this other type of probe, the quench, where you shock the system out of some low-energy state to some locally correlated to high-energy state, and then watch it equilibrate. Actually, I should have mentioned that for this system, we can also do the numerics on spin systems. And again, for systems of up to size 14 spins, one can plot this type of curve, and it looks a lot like that. Okay, yeah. Well, yeah, this is another thing that you can do, to take all of a sudden a high energy state that's very, very far out of equilibrium. In that case, you might not have this feature that the entropy is small to begin with, so it depends on what the Hamiltonian was that you were using to begin with. Okay. So now, let me give a quick introduction to chaos. So first of all, we've been discussing so far relaxation to equilibrium. Decay is two-point functions, saturation of these entropies, but in real-time dynamics, there are also features that are growing with time, exponentially growing with time. This is something that studies classical chaos in sonics. So in 30 seconds, what I know about classical chaos can be summarized by thinking about this classic problem of a particle moving in a stadium that looks like this. This is a classically chaotic system. What that means is that if we take a particle, let's say it's here, and it's going that way, and plot its trajectory, so it has some kind of a path. If we could displace the particle a little bit first, and then set it moving, it would have had a very different trajectory. And for this type of system, the displacement delta x of the particle's trajectory before and after we perturb it, as a function of time, will be growing exponentially in time, where the rate of exponential growth is called the Lyapunov exponent. So this is classical chaos. We would like to have some understanding of this in quantum mechanics. Actually, it's worse than that. This only happens for a much shorter time. This only happens until, let's say, delta x gets as big as it can. So in the stadium, delta x can only get as big as the stadium. That will happen in a time which is like, the laws of the initial size of the perturbation, which is much shorter time than any of these quantum ray times. Okay. Yeah, so there was this nice paper written about this in 1969 by Lukin and Ovchinnikov, who pointed out that you can see a version of this classical chaos in a semi-classical quantum version of the system. So what they did was they considered the commutator of a momentum operator T with the momentum operator for this particle at time 0. So T is T with T is time 0. They argued that in a semi-classical limit, this should be equal to IH bar times the Poisson bracket. So T is T, T is 0. Okay, and the Poisson bracket. Probably I'll have to sign backwards. But so let's work out what that is. In this case, actually only one of these terms contributes. It's the term where, it's the second term here, where the derivative with respect to the momentum is saying this factor. That's because the derivative with respect to position of this guy is 0. So what we get is minus I h bar times the derivative of t of t with respect to q of 0. This is asking the following question. Suppose I take a trajectory, and I look at the momentum at some time t in the future, given the initial positions. Now I change the initial position of the particle a little bit, and I ask what the new momentum will be at time t. And we've argued that these perturbations in these chaotic systems grow exponentially with a time scale set by the Lyapunov exponent. So we expect this to be proportional to h bar times something which is exponentially growing, e to the minus l times t. An important feature of this is that the sign in front of here can be both positive and negative. Momentum can be more in this direction or more in that direction, depending on exactly what initial condition we're talking about. So if we average this quantity over the thermal ensemble as it stands, we're going to get something which is 0, or at least very small. So instead what we can do is we can consider the square of this quantity, and then average it. And then the sign that appears here will always square something that's, actually it will square something that's negative because of the factor of I. So we can consider this quantity, t of t, t of 0, squared. And now we can average this over the thermal ensemble. Our expectation based on this argument is that in a semi-classical system, this should be proportional to minus h bar squared times e to the lambda L t, where lambda L is the Lyapunov exponent of the classical system. Oh, sorry, we should have done this. Yes, absolutely. The interpretation of this is somehow that t of t and t of 0, they almost commute because we're in a semi-classical limit of this one system, but they don't quite commute, and that effect is something that grows exponentially as a function of time. Okay, so we can generalize this outside this single particle stadium picture to